Passcode. I have to select passcode or waiting room, unfortunately.
Yeah, I think you do. Welcome to the P2 Live Forum. Today's April 21. It's 1 p.m. Pacific. And we have a pretty good group online already. Today, pending success on chip's end with some code that was working and then got broken, we'll be talking about controlling this hoverboard motor. And it's interesting history behind our desire to do this, which is really motivated by having a new type of motor, a powerful one with good positional control for mid-sized robots. Like you might be familiar with the Arlo robot. And that robot we discontinued, but we plan on making a P2 based motor controller. And so we've assembled a team with Chip and a gentleman named Doug, who probably isn't here today because he has a day job, and then also Michael, who did the circuit board. So Chip's making some preliminary headway and trying to apply the P2 to this. So if he is able to rejoin us and his code works, we'll get an update from him. Zoom fiascos. So I'll spare you the 2 hours I had online with support today, but this is what the result is. At 1:55 today, that specific time, we have to switch over. I have to leave this meeting, which basically ends this meeting, and go start up an educational meeting with Andy so he could show a bunch of teachers how to program robots. And this is okay. So what we're going to do with the help of Stephen is we will paste a link in chat, which was just pasted in here. And we'll refresh this topic before we end this meeting so that people can be sure to get that link and then go to the new meeting. So that'll be at 1:52 or 53. I'll have to end this meeting. Very sorry for the inconvenience. Getting out the credit card and messing around on chat just didn't solve the problem today quick enough. So thanks, Stephen, for coming to the rescue.
Yeah, you're welcome.
That's great. Upcoming meetings. We got some good things planned right now. So you'll notice the rest of May is planned out with four topics. And by the way, before we talk about these topics, I just want to urge anyone that has anything they want to share to let me know, and so I can put it on a calendar. And don't let the sometimes very high bar that has been set by others inhibit you from sharing. You can share something for 5 or 10 minutes, and I will present it accordingly so that there's not a lot of pressure on you to have anything prepared. You can just talk about a project you're doing or an idea, or share something you've created that's more substantial, doesn't matter. But the point is, it's great if we know some of the main discussion areas before we get here to each meeting, even though we can talk about everything, because our attendance is usually double when we have some kind of topic. So April 28th, next week, Johnny Mack is going to show us Sony infrared communication protocol in the P2, and this is very effective. I've seen it working with 20,000 DEF CON badges and people in a room wandering around, sending and receiving their names and whatever phony information they put in their badge. And John has a lot of experience with these particular parts. And there are 2 components you could get if you want to run this. It's these infrared transmitters and receivers, and I can paste the link on our site after, or in the chat after we get going here. And then May 5th, we'll bring you current on the documentation work being done at Parallax with Jeff. And that's for the Propeller manual and the data sheet. Jeff, Michael, and Chip, and Stephanie, but certainly at least Jeff will be here for that. And talk about the P2 Edge revisions in more detail and whatever else is on everybody's mind. May 12th, John will show us how to retrieve the signals off of one I/O pin from this FlySky S-Bus transmitter with receiver. This is a $59 cheapie you can get from Amazon, but it's very popular with control of props and things. I'm actually going to be using it on a larger boat project that I've got in the works. So I'm looking forward to his code. So it's a good way to get from human to some kind of machine control. And then this is a good one too. This just was hatched today. So we have a professor named Gavin Garner who is writing a book on the P2 and creating a lab. And you're looking at these lab kits. He's made 100 of these. And he's going to show us his lab and talk about how he's using this in his mechatronics class. And this is really cool. So he's a real hard worker. He's been using parallax for 20 years. I think he learned on the basic stamp. So we'll hear from him. And just small stuff. The elusive cable that we've been talking about since November that I ordered and we designed, which is kind of a USB cable that can transmit some serious current to the Johnny Mac board. These are just really late coming from China. There's no one that makes this cable in the United States. And it's taking forever to get things from China because ports are backed up and there are other complexities now with tariffs and shipping costs, yada, yada. So I don't mean to sound like I'm complaining, but this is 6 months now to get something really simple. And P2EC, just briefly on this, and Chip can really go in detail because this is the first I've seen of these today, although I'm aware of the changes we're making. We're making 2 revisions, actually 1 new product and 1 revision. The revision is to the P2 Edge, which will become Rev C, and it has the improved power supply to accept a much wider range of voltage, 4.5 to 17 volts. So you can plug in most whatever wall warts you have laying around into your Johnny Mac board and not blow these up. And then it has a very accurate clock. And let's see, dip switch and flash memory.
Hey, Ken, can we stop there for a minute?
You bet.
Yeah, so what we've done is we have to run an oscillator in order to deliver sharp edges into XI in order to get around a potential problem where a customer is switching the 28 to 31 pins rapidly and causing some power supply collapse on the die. And so the trouble with the sine crystal oscillator is that it's only slewing at like, I don't know what the slew rate was. I think it was like 10 nanoseconds per volt, 1 volt per 10 nanoseconds. It was very slow. So when these high-speed shocks would come in on the power supply, if it was crossing the threshold, it would register extra edges and that would throw the PLL off. So we have to do something where we drive a sharp edge into XI to get around this potential problem. This is something we'll have to make an errata note for. But on this board, we don't want to have any caveats for the customer. We just want them to, if any of us are designing a custom product, we can easily avoid that circumstance on those pins. But we don't know what someone's going to do with this. We just want all the IO pins to be the same. So we have to deliver something sharp. So we have a little inverter here. This could have been drawn as an inverter. You see the 74 LVC 1G04. That's just a sharpener. So what we have down here in the front of that, in front of the 1000 puff cap is an oscillator, but we're going to run this thing at 1.8 volts because that keeps the current under a milliwatt. If we had a 3.3 volt oscillator, it would take a lot more juice and just jack up the quiescent current of the whole system because we're not going to be throttling this thing off and on with an enable pin. We're just going to let it run. But this particular part here is a pretty cool part. It's an Epson thermally controlled crystal oscillator, and it's like 500 parts per billion error. So it's half a ppm error. So it's super accurate. This is what JMG always wanted after he petitioned so much for the, what do you call it? The reciprocal counter that can quickly measure frequency. So this is like instrumentation grade right here. It's going to be very good. So what comes out of that thing is only 0.8 volts peak to peak, but we couple it through this 1000 puff cap, and then we run an inverter that's kind of biased to its, with its feedback resistor, the inverter is biased towards its threshold. So just knocking that cap up and down It worked with much less than 800 millivolts, which the clip sine oscillator outputs. But this is going to give us a nice sharp signal into Xi that'll base.
We
So
lost
that's
you.
going to be on all.
Repeat that nice sharp signal into Xi.
Yeah, and we have a very accurate time base now.
Nice.
And I calculated half a ppm is about 15 seconds per year.
You said the design's reduced to 4 layers. What was it before?
6.
Wow. Okay.
And so it was, and see, there were issues there too, where some of it was made up of 3 boards that were like paper thin. So there was a lot of coupling, between like 1 and 2, and then 3 and 4, and then 5 and 6. So that's going to be, I think we can make the stack up so we spread those out better now.
Nice.
And but when you go to like super high layer boards, you wind up with these layers that are very thin, and they bring signals too close for comfort, on top to bottom vertically. Okay, that was that, Ken. By the way, I just got the motor thing running. I can't believe it. I was just pulling my hair out. I had the thing working earlier today, and I thought, well, I'll just combine it all into one cog because that's nice to have. And then I had pulled in a wrong ADC configuration value, and it was like, it was not working, but now it's running. So I have something to talk about after all today.
Cool. And Chip, before we leave this P2 Edge, we're doing 2 things. We're making revision, and then we're also making the RAM version. And we're just doing these in parallel.
Yeah, so what you see on the left is the PS RAM version. That's going to have 32 megabytes across those 4 chips on the right. So we have a 16-bit wide data path that'll go from, it'll use that pins P40 to P57. It's 16 pins for data path, and 1 for chip select, 1 for clock. And then Roglo on the forum has been developing drivers for that and proving out the concept, but it's been kind of hairy because he has this flying lead for the clock and chip select. And at these frequencies, that wreaks havoc. So this is going to be a very tight layout. It should work very nicely. We're probably going to add an R and a C on the clock pin so that we can give it a little bit of phase shift. And we can populate that with a shunt if we don't wind up needing it after all. But all the IO on this is over 2 internal clocks. It's not double data rate, it's single data rate. So it's safer to begin with. And then we put on the left, you can see there's 2 identical looking switchers. We found some inductors which are molded so they don't have this problem of having these big ceramic hats on top that can become broken and change things. So we have a 1.8 volt and a 4.3 volt, I think he made it, regulator. And these are switchers. So this thing's going to take up to like, I don't know, something around 15 to 20 volts DC in. Excuse me, it'll top out there. You can run it as low as 5, but you can also put in 12 or 15 or 16 volts. So it's going to be a lot more easy to work with for industrial stuff. And then otherwise, it's the same thing as we have now, just better switchers, wider input range, more stable clock. And in this case, we have the PS RAM on the right, but the other version will not have anything there, I think. We're just going to route those pins out to the connector. And then on the back side, we have the, what is that called? It's a micro SD
SD socket, optional for the customer to install.
Right, which uses the boot pins that are shared by the flash. So like Ray or Clouseau on the forum, he loves using SD cards. So he would just plug something into that and boot from it if he were to use this, of course. He may not because he has his own board.
Chip, are you making the same clock crystal feed to this board as well?
Yeah, yeah.
Okay.
Yeah, but I don't know. What we're going to do is put the land pattern on for that SD socket, and someone can solder it if they want it. It's pretty easy to solder that thing on there, but it's a backside operation, and most people aren't going to want it, but if anyone wants to, they can solder one of those things on. And
it's the pins and the shield at the other end get soldered, right?
Say that again?
It's both the pins and the shield that get soldered to give you a mechanical.
Oh, yes. Yeah, and I don't think that has any through hole, right? It's all surface mount. I mean, there's nothing in there that has to dive into a hole.
Nice, that's pretty easy.
Yeah,
Okay,
yeah. So that's the future of the edges.
cool. And then just brief update on this Hub 75 panels.
Oh, you're fine.
This is your video, Stephen. But anyway, these panels I ordered in November and they just came in. So another 6-month lead time from China, but now we have a regular supply going. So we have 100 of them. And there's some confusion over the cables that come with them, but I've got that sorted out and extra cables are coming. So that you'll have a power cable and then a harness for each one. And anyway, so they're in stock. We just have to get a web page up. So Friday, Stephen, when I meet with you, I can get a few more details from you to present these properly. But I think they're going to be $38. It's kind of where they land.
Nice.
So before we start today, just to take a quick inventory, I think we have one quick show sharing from Carrol Moore. So we could do that first. And
Yeah.
okay. And if there's anything else to be shared that can't wait until the discussion afterwards, you could just tell me right now. Is there anything else that's quick show and tell that we might throw in here? Okay, then Carrol, do you want to do screen share or
Yep, I've never done it before, but let me give it a shot.
just look for that green button on the bottom? And then you'll be able to choose from an application or a whole display.
Okay, let's see.
Just don't want you to give away your banking password.
Yeah, see my screen?
Yeah.
Yeah.
Okay, you see the propeller tool up?
Mhm.
Okay, there we go. A couple of weeks ago, I was looking at some videos of the new cockpit displays they're going to use in the Orion spacecraft, the Boeing Orion spacecraft. And I thought they were interesting because I used to do that work when I was over at JSC. So after I saw Johnny Mac's demo on the ping that y'all put together that had the little box that moved up and down, I said, that's kind of interesting. I wonder if Debug could actually draw the Orion displays. So I spent a couple of weeks and this is what I come up with. Let's see if I can get it up. I got an interesting green bar here that I don't normally have. I wonder if,
The green bar is the zoom window, probably.
yeah, that's probably a zoom window.
Oh, that's the raw debug output, isn't it?
This little green bar right here. Do y'all see that, or is it just something I'm looking
We
at?
do. Oh, that's only for you. That's the zoom control.
Oh, yeah, that's
I
at
see
the
what
top of
you're
your
saying,
screen, right?
Okay, so y'all don't see a green line going right through the center of the display.
No.
We don't.
Okay, good. So this is basically a 480 by 800 debug display, and I created two of the Orion formats. So this is actively being drawn by Debug.
I can't tell if we have half of that display off screen.
Yeah, it might be
click on those
reshare.
windows.
Oh, that helps.
Oh, so maybe I'll put it in the middle.
Yeah,
There you go. There you go.
Do you see the full 480 by 800?
we're missing the
that's amazing.
bottom.
Oh, missing
Lift
the
it up.
bottom?
Maybe lift it up a little bit.
You're missing part of the bottom one.
Yeah, the bottom.
Oh, I see what you're saying. Now I know what that light green bar
Oh,
is.
it's the
Is there something
boundaries.
I can do to show my full screen?
There is. Just do a new share and then choose your display.
Okay, so let's see.
That's looking great, though. My gosh.
Let's see, where is it at?
It's under the same share screen, and when you go there, in the upper left, once you press on that green, you should see an option to share display,
Share display.
and that'll share your whole desktop.
Let's see. I see the screen. Is it called screen?
I think that's what it's called. Yeah, screen.
Y'all seeing my full
There you
screen
go.
now?
That's more like it.
Okay, you seeing the full display?
Mhm.
Well, let's see. It's window.
Perfect. Yeah. Now you can arrange things. We'll see exactly what you're seeing.
Okay, great. So yeah, so that's the way the one display in the Orion actually looks. It's divided by what they call the tabs, and then it has an upper region and a lower region. And this current display in the upper region, it's displaying an EPS summary display, and in the bottom region, it's displaying what they call a GNC switch display. First of all, I wanted to state that none of this stuff that I've done is from proprietary information. This is all from public information I was able to glean off the internet. And last Friday, I dropped a zip file of all this code and a rough project plan on what my plan was and how I was going to, what I was going to do with this. And in the plan, there are links to all of the public information that I used for this code. I want to make sure there's no conflict of interest with this work and some other stuff that I have going on out here at JSC. So, but this is actively being refreshed. This isn't a static display. And let's see,
Fun.
right here, this is the main body of the code in the top object. And you see all it's doing is it's clearing the screen. It's drawing the tab section in the middle. Then it's drawing whatever format I tell it to draw in the upper display, and then whatever format I tell it to draw in the lower display. And it waits a second, and then it increments the clock that's right in the center, which is nothing but an elapsed timer right now. I haven't tied in my real-time clock yet. And then it just repeats the process over and over again. Now, what I did this week that's not in the last dump from last Friday is I added some buttons. I took that little 4-button accessory card that y'all produce, and I built a little driver for it. And what I'm able to do with it, if you look up in the ESP section in the upper left-hand corner, you'll see a battery 1 and a battery 2. Switch is closed on battery 1, switch is open on battery 2. So with the buttons I have, I'm able to change the switches on the 2 batteries.
Nice.
And in the bottom display, in the GNC display, these darker green boxes, I'm assuming from work I've done in the past, these are areas of interest to the astronaut where they can move to the dark green box and select it, and then it'll bring up some additional information for them. So what I did with the other 2 buttons on the accessory pad is I just built the ability to move through those boxes. Let's see, let me go the other direction here. And they seem a little slow because the display's only refreshing itself every second. So what I'll do is I'll hold down one of the buttons and you'll see it'll just move through these boxes. And because of the way they plan on selecting these boxes on orbit, it's not a rectilinear type selection, left, right, up and down. There'll be code that will make the decision on which box they're going to go to next when they hit the up or down button. And I kind of built that into the GNC display. This is basically the feature right here. This is the route that it follows when you hit the up and down button. Let's see. Bring it back up. And you're able to actually change the ordering and take things out, you know, if you don't want them to go to that particular box. So those are the 2 controls I have right now with the 4 buttons I have. But my ultimate plan is I'm going to build a front. I want to display this eventually in a 7-inch HDMI display that y'all sell. And then I'm going to build a custom frame around it that has the 11 buttons on each side and the 7 buttons top and bottom. And then I'll have a fully functioning display at that point. So, but what I was amazed at when I did it is how fast the P2 is able to compile the code and throw up the debug window. It's that fast. To me, that's pretty fast to do that.
It's stunning.
Yeah, we make efforts to try to keep it simple so that it can work like that.
Right. So it's refreshing right now at a rate of once a second. But as you see, what I'll do is I'll make it refresh at a rate of about once every millisecond. And you see it's still solid at once every millisecond. And the buttons are a little bit faster because they have, you're dealing with you're dealing with bounce at this point. But let's see.
Carol, we need to add a bar to the, the thing that spits out the raw debug information. We need to have a little bar on there that shows how full the buffer is, because it might be pulling in a lot more data than it's displaying. So if you hit reset, if you hold the reset button down on if you have a reset button on your project, see if it doesn't actually stop. This is how you know right now if you're real time or not, because there might be so much data queued up in the PC that it can't draw these screens over and over. It's getting the commands.
So what do you want me to hold down when you say reset? What exactly you want me to hold down?
Well, you can just like unplug the prop plug and then see if you keep getting this displays updating.
Okay. Well, I mean, it's sending the data to the IDE, isn't it?
Oh, it is, yeah. But what's happening is I think it's spooling up. It might be, if you're going at 1 millisecond, it's probably spooling up that data in the PC, and then it's rendering it as fast as it can on the PC end. But with the these 24-bit pixels on these like plot displays, on all displays really, it takes a while for the PC to do all the rendering.
Well, can you tell if I hold down one of these buttons and it scrolls through the little green boxes, how fast?
Oh, well, that would mean it's real time. Yeah, if it's responsive, then it's real time. But if you notice, there's a lag.
I'll hold down the button and we'll see it scrolling through the green boxes. Let's see. Let me restart it here.
Yeah, it'll work at first, and then the delay will get longer and longer. If
I see what you're saying. Okay, let's see. Okay, wow. So you see it moving through the boxes?
Yeah.
So you're saying at some point it's going to stop?
Well, yeah, now go the other direction and see if it turns around.
I see what you're saying. There is a delay in it.
Well, because what's happening is, all that data you shipped off to the PC, the PC is going through it as fast as it can, but it can't redraw everything at that 1 millisecond rate.
So what would be a decent rate to run it at?
Oh, probably like 10 milliseconds would be fine, or 20 milliseconds. It depends on how much, it's a function of how much stuff is being drawn.
Let's see.
But what we need to do is put a little like progress bar looking thing at the bottom of the main debug window, so that it will always tell you how much, if any, is queued up. So you can see like, oh, well, it's got like, 8 megabytes queued up that the PC is still trying to render.
Oh, okay. I might have to work with you on putting one of those together.
Yeah, it's something we need to add to our apps, because only we know how much is, what the spooled up data versus what it's actually processing at the moment is.
Okay.
And this will become really important when we get the thing working 2 ways. Because then you're going to see right away if there's not a response, or if it's not responsive to the PC.
Okay, I got you. But that's basically what I had. And one more little thing I'll cover, if I can get this down. This is how I divided up the work here. I've got the main display controller that throws up the debug window, and then each one of the formats is in a separate spin file. And if you can see right here, I can reverse the order. And let's see. Oops.
How much code does it take to do that? Like, I see it's about half comments.
How much code in the stored on board?
Well, how much code, like if someone is watching this and thinking, well, I'd like to do something like that, how much work are they looking at?
Well, the EPS display was the easiest one to do, and I'll show you the code for it. And the reason for that is I was able to, when I draw the boxes, they're like a method. I have one method for like drawing a battery box, but when I draw multiple battery boxes, this is how I draw the multiple battery boxes right here. I just give it an X, Y, and then I give it, you know, the data items that it's going to be displaying, and then it just draws the box.
Sweet.
So,
You're welcome. Okay.
so this was pretty, this was pretty easy to build right here. So that's the EPS display here. And let's see, the code starts right about here. This is the code for the GNC display. So
Yeah, it's not a high volume. That's amazing.
no, and let's see if I can get this bar out of my way here. Let's see. Come on. This is how much is inside the P2. It doesn't take up a whole lot of room.
Wow.
So I can put probably a whole lot of displays on it. What I'm going to work on tomorrow is Tubular was talking about the tab spinner. They call it a Twizzler. It's basically just a quadrapture encoder. I'm going to add one of those tomorrow, and hopefully what that allow me to do is I'll be able to scroll through these displays with a spinner, and you'll see in these tab sections, you'll see the display, and then go across the tab section, and then you'll see the upper and lower displays being changed as I spin it with a spinner.
Nice.
Super
So-
cool.
Now I see you've got all these like little colored backgrounds, and like this one with angles is kind of interesting where it says G0/0.
Yeah, that's the GMT timer that I'm going to tie my real-time clock into.
Okay.
They basically display time in just the GMT days from the beginning of the year. And so you caught the angles, huh? Because you don't have any graphical elements in your plot to do these angles.
Yes, I'm wondering, how did you get them to fill in without bleeding the color from the other boxes?
It's an optical illusion is what it is. I have three boxes, a gray, a black, and a green. And then the two vertical white lines, they're 5 pixels wide.
Oh,
but
they're
I
fat
scan
enough
them
that they
over.
just cover it.
Yeah, they cover up the transition between the boxes.
Yeah.
It makes it look like it's at a slant when it's not really at a slant. Because that's how the tab, that's because it's tabs is what it is. It's supposed to be illustrating tabs. So, and let me
And
see.
effectively pointing to the display.
What's that?
It's effectively, the tabs effectively point to the display, so you know how to associate the names to the display as well.
Correct. And let's see, one other thing, and it's besides just the stuff that I've shown moving, I do have some variables. Let's see. Yeah, there's some variables in here. Let me pull up something and just show you. This is on the GNC display. See, it's got these things called the pitch left controller 1, 2, and 3. So I can just throw some values in here. And yeah, you'll see where the variables are right here. So that's the next step is after I do the Twizzler, I'm going to do a data generator running in a cog, and all it's going to do is it's going to spin all the data through its low high values so that you can see the display being updated. So I thought it was interesting. It was able to do exactly what I wanted it to do.
That's good. That's good. Yeah, I'm glad I did all that work to make that anti-alias shape and line drawing, because that helps this to look better. If this
It
was
does.
all pixelated, it wouldn't have been so smooth looking.
Yeah, and I did notice when I blow it up to actually check down at a pixel level, it's interesting if you get like two color lines close to one another, like a white line and a red line, they kind of, the color kind of blends into each other. Which is
Yeah,
kind of,
that's all that anti-aliasing stuff.
yeah. So let's see, I'm trying to think of what else I'm going to do with it.
Any questions for Carol on this project? I put the forum link in the chat.
Okay, I'll do that. And
I already did it for you.
Oh, you did it? Thank you.
Yeah.
Appreciate it. All right, I'm done.
Oh,
Thanks, Carol. That looks
Super.
great.
it's good looking work, Carol.
Thank you, sir. So let's see, I'm going to stop sharing.
Okay, so before we go on to motors, I'm pasting into the chat right now something you're going to need in 20 minutes exactly. So copy that in a notepad, because when we end this meeting and you all go to the new meeting, courtesy of Stephen, you're going to need this information. So you'll have to copy it out of chat and put it somewhere where you can get it. Otherwise, you'll get lost on the way. Okay, Chip.
All right, let's see. Let me pull up the schematic here. This is an important thing. There we go. Okay. Doug just sent me. So Doug is a guy that we used to work with at Parallax. He worked for us for, I don't know how many, 3 or 4 years. You remember, Ken?
Yeah. He made
And,
the ping sensor.
Yes, he designed the ping sensor that we still sell. Let's see. Boy, this schematic doesn't show. Oh, he didn't send me the part of the motor control. Okay. So let me see if I can just pull up on the net. Let's see. BLDC motor drive. And because all these schematics for these things look all the same, what you have are basically kind of like, here we go. Okay, I'm going to share my screen. Okay. In fact, we'll use this one here. So in a brushless DC motor,
Lots of
things
real-
are kind of inside out relative to most motors that, ooh. Oh no, where did it go? Here it is. All right, now. Okay, so you can all see this, I assume?
Mhm.
Yep.
Okay, so you know, in a normal motor, I used to take them apart when I was kids, and they always had brushes, right? And so as the brushes would energize some electromagnets, which would pull towards some permanent magnets in the outside of the motor, and then as that thing would advance, the brushes would then touch new, what are those called, stators, or they're electromagnets, and then they would pull towards again the next magnet. So what we have these days are all these brushless DC motors, which is the same concept, but instead of having brushes, you use electronics to switch current to the electromagnets, and then the permanent magnets are on the outside of the motor, but the outside of the motor rotates now. So it's kind of like, I think most of you are familiar with these things, but it's not quite a normal motor. It's reversed in the sense of where you hold on to it. It used to be that you'd hold on to the case and the electromagnets would spin. Now you hold on to the electromagnets and the case spins and the axle attaches to the case. But the really neat thing about this is that there are no brushes to wear out. You just have like nice little ball bearing races on either end of the shaft. And these things can be sequenced with a lot more efficiency than brushes worked with. And so what you have are 3 legs, and everything kind of boils down to this for 3-phase motor control. You have a set of, you have 3 wires, U, V, and W, and then you have a high and low side switch for each of those wires. And this can be, you can pulse modulate these things. It's always set up like this because there's no sense in generating super high current analog signals. So instead, you just switch FETs. And in the case of this little board I have here, see, I'll stop sharing for a minute. And I'll take my camera over to here. This is our board, right? So those 6 FETs, like here's a high side switch, low side switch, high side switch. Whoops.
Move the camera up a
There we
tad.
go.
That's better.
There we go. So here's a high side switch, low side, high side, low side, high side, low side. So this is maybe U, V, and W wires. And in this case, Doug found a really cool little 8-pin chip. It's a it's like a high side NFET driver. And what it does is it uses kind of a charge pump to create a local floating supply. So rather than have like an NFET for low and a PFET, which is not as efficient, not as low of resistance, it uses NFETs for both the high and the low side. And then this little 8-pin chip here, which is sort of hidden, generates this 600 volt potential offset, which you control digitally from, you know, the safe side of this chip. So this allows you to use 2 super low impedance end devices for both high and low side switch. And these chips are, I think they're like 80 cents or something, but it's a very nice little invention. So it's preferable to use all the same devices. So what we do is we run PWM into these things. Now these particular FETs are crazy. They have super high, we're ordering some lower gate capacitance FETs. These things are like 6 nanofarad per gate, which is huge. You know, what would be more ideal is like maybe 100 puff or something. So these things are so heavy to switch that it really limits our ability to sequence this thing very quickly, because what we're doing is we're PWMing the gates of these MOSFETs, right? So the current averages out, but we're hard switching them off and on, kind of like a Class D amplifier. But the topology of all this is pretty darn simple. And then here you have these 3 wires coming out that go to the motor, right? And right now I'm running it. You can see that, you know, you get very graceful operation of any size brushless DC motor because you're actually controlling the three phases on the fields. And we can go faster than this, but with these big giant FETs, we can't go much faster. Now let's see, share the debug screen for this. Let me screen share again. All right. So here we can see the 3 phases that we're outputting. And then we have some little shunt resistors near ground that are really nice for sensing on the low side the current. Because remember, each of these 3 wires alternately sources and sinks current. So we're using ADCs to measure each of the 3 shunt resistors. And so what you're seeing there, that modulation is actually the PWM, right? It's sampling sometimes when the PWM. To make this thing look, I had this thing earlier before I took it apart and put it all into one cog today. I had just single lines that were just ultra smooth because I was measuring over the entire cycle. So I was getting a very nice average. But there are some things we have to develop yet in order to be able to take that current data. And maybe we also need to measure what's going on at the wires, you know, digitize those too. And we need to figure out ultimately where the motor position is relative to the permanent magnets. Because this motor, every 16th of a turn goes through a 360-degree electromagnetic phase, you know, where we commute all 3 phases and the motor steps 1/16th of a revolution. So that's what we need to do. And then once we know and I don't know how that's going to work. This stuff seems kind of like black magic, but Erna on the forum has been talking about it in pretty simple terms. And there's many, many videos. We've looked at dozens of videos on what's called field-oriented control, where you you use the 3 wires as your outputs and as some kind of sensory input to determine where the motor is, and so that you can apply your torque at 90 degrees off. You always want to be 90 degrees in advance of the magnetic poles in order to get maximum torque. So you get the most use out of the power you put into the motor. So what we have here anyway, let me move my other screen down. I'll show you the program. Any questions so far about this?
Just a comment, Chip. Yeah, Bill pointed out it's called a brushless outrunner, in case someone hasn't seen that. And if you're looking for the motor, the wheel is the motor. It'd be fun if we had one of these that you could see from the taken apart perspective.
Okay, hold on. I've got, let me get a picture up real quick.
All right, and while you do that, I've ordered 100 of these on a slow boat. And at the current rate, we'll see them by September.
So you've ordered 100 of the wheels?
100 of the motor wheels, yes.
Oh, cool.
And in anticipation, since they've demonstrated we can control it, and Chip has plans to get either the feedback from encoders or the feedback from the FOC approach working, we've also made a bearing block. So you can put this on mid-size robots.
Cool.
Yeah, and let's see here if I can get this image. Well, let's see.
Will you also be able to sense the amount of energy needed to move?
Sorry about that. Let me just relocate the window up here temporarily. You can see how this thing works. If you've ever
Chip,
seen these.
Can you also measure the current through this feedback?
Yeah, we can definitely measure the low side current, right? And we can figure that the high side current is complementary to that. So I don't know that there's a need to monitor the high side at all, but we can do it with shunt resistors on the low side. But there's stuff we don't know about how this all works yet. I mean, and you know, if you've ever noticed these electronic speed controllers, if you've ever used them, like for a quadcopter, they seem to want to like ping the propeller a little bit. You'll see the propeller move maybe a quarter turn, and there's some significant startup time for the ESCs. I think what they're doing is they're learning the motor, because you can't be assumptive about just sending 3 phases out. You have to be able to have some awareness of what the motor's reluctance is, its back EMF. So you have to tailor your driving approach to every different kind of motor. And that's why ESCs have long startup times. And someone on the forum, I'm sorry if you hear it, I can't remember who said it, but they said that there's a group that has developed a lot of this stuff for RC models. And they came up with all these techniques for pinging the motors and kind of learning about them so that they can drive them. And then subsequently, you know, the Chinese made they used a lot of that know-how to make all these inexpensive electronic speed controllers that you can buy for like $10 or something. Now, if you see that picture there, you see that the permanent magnets are on the outside, and you have all these electromagnets on the inside, which are stationary. And this is held together with a lot of machined metal with bushings and bearings. So it's pretty load bearing. And the tolerance is like maybe 25 thousandths between the electromagnets and the permanent magnets. But the cool thing about this configuration is it is super torquey. There's no need for gears. There's no need for like, you know, a high RPM motor that's geared down that has all this backlash and inertia. It's completely direct drive. So if you've ever seen these kids running around on these silent hoverboards, this is how they work. They're completely quiet.
Chip, when I ordered these from the supplier, is the first time where a supplier in China wasn't ready to send a load over, because I told them the application and their response was, huh? Robotics? These are for hoverboards.
Right. Yeah, it's easier to use a hoverboard than a robot. So more robots or more hoverboards.
So the motor he's using is a 6.5 inch. I can get a link to it and I'll send it to Chip to post. So right now, everybody, we got to switch over to another Zoom meeting.
Oh, wait, let me get I haven't gotten the link. So we've all got to get the link, right?
So it's in the chat.
Okay, hold on. I'm going to stop the share.
Everyone just click on the chat and you can go find it.
And I will have to leave and start the meeting so everybody can get in. So.
Okay,
Okay.
they'll see you in a
Okay,
bit.
so
let's see
copy
all-
that last data and maybe drop it into Notepad or something so that you can, if you need the extra info, you can get it.
And we'll just give this 30 seconds or a minute more so everyone can find it. People are already leaving, so I guess we're getting the idea.
So Ken, we'll be able to build a two-wheeled robot, kind of like the Segway.
Yeah, that's the idea.
Cool.
And to my knowledge, I've only seen one